Hello, everyone, and welcome to today's exciting webinar. I'm Tim Stark, and I'm the host of today's exciting event. I am a professor of civil engineering at the University of Illinois at Urbana-Champaign and the technical director of the Fabricated Geomembrane Institute. This is our second webinar of 2020, and the remaining 10 webinars for 2020 have already been scheduled with great speakers and timely topics, which I'll at least share the next webinar with you at the end of the webinar today. You can go to the FGI website and register for these 10 webinars if you'd like. Today's broadcast, during today's webinar, we welcome questions and comments which can be typed into the question box in the control panel. You may send in your questions at any time during the presentation, and our speaker will address these questions at the end of today's presentation. The recording of this webinar and a PDF of the slides will be made available on the FGI website after today's presentation. PDH certificates will be sent automatically to all who attend the entire webinar. Today's webinar speaker is Graham Fairhead. Graham is the Managing Director of Fabtech Australia, based near Adelaide, Australia. Graham has been designing and installing geomembrane liner and cover systems for dams, reservoirs, irrigation channels, ponds, canals, and tanks for many years. Today, Graham will focus on floating cover systems. Graham is also the current president of the Australasian chapter of the International Geosynthetic Society, or ACIGS. The title of Graham's webinar today is Floating Cover Systems for Ponds and Reservoirs. Graham, thanks for squeezing this webinar into your busy schedule and joining us from Adelaide, Australia. The webinar is now yours.
Thanks, Tim. And you can see the slides okay, Tim?
Yes.
Good. Okay. So here's just to start. Here's an example of a floating cover. This is in South Africa, Cape Town, the Western Cape, Simonstown. It was provided by our friends at Aquatan. It's a concrete water storage reservoir, polypropylene floating cover installed a couple of years ago now, 2017. Originally about 30 years ago, built in CSP. I've got a couple of interesting examples. This is somewhere that I need to move this. Excuse me. This is interesting. It's kind of halfway between Australia and North America, the Marshall Islands. This is actually Margero. You can see at the back here a runway. This is a water harvesting system for that runway. In the foreground here is water storage. You can see there's a wall here. It's being lifted to create more storage. And here's where the floating covers are. We built these about 6 or 8 years ago. And here's my supervisor here. I like this photograph. We had great difficulty getting Dean back from that particular project. Another example, this one's from North America. Doug Hiltz sent me this example. He was the engineer of this project. It's built in CSPE, very large storage, relatively common, these large storages in North America. This is nearly a gigalitre of volume, 70-odd thousand square meters of material. And then a couple more here, examples of floating cover storages. On the left here in Israel, in the Middle East, Israel's interesting. Most of the water in Israel is desalinated water. It can be quite aggressive with lining materials. It's chlorinated, so it's quite difficult for the materials to handle. Very, very high UV in the Middle East. This was built in 2006 using EIA materials, about 30,000 square meters of material. And then on the right here, we've got an example from Europe, Mediterranean Spain, southern Spain. The evaporation levels there are around about 1.5 meters a year. In this case, it's an olive farm irrigation storage made out of polyethylene. Tim often refers to simple covers, and this is probably an example where it's been built to a price. Very simple features on the covers, not particularly expensive materials. I'll point out also here, you can see on both of these, the tensioning system here is a central, what's called a central plate system. Kind of follows the toe of the dam when the cover's low, and equally here you can see there's a kind of central plate configuration there. So, just to introduce the topics I'm going to talk to, briefly talk about some differences between Australia and North America. Applications for floating covers, where they're used, talk about the design of static covers and dynamic covers, materials, construction, managing asset life of covers, and a few case studies. This is quite a good example here of a sophisticated, complicated cover, the opposite to the Spanish example. This is potable water made of EIA materials. You can see the ballast line through the middle here that's creating tension in the cover, floats either side. Floats on the right hand side here are providing a walkway as well. Another float system through here, vents, covers sitting very well, nice and taut. Good example of a well-built cover. So comparing North America and Australia, I suppose the first thing is population. In North America, about 20 times more people, so I guess there's about 20 times more water, 20 times more water assets, 20 times more covers. But more critically, the important thing is probably here on the right-hand side. So you can see the UV loading in Australia, red, very high here. In the Middle East, that Israeli example. It's similarly in the south of North America, but up here, of course, it's cold. Illustrated here, we don't have to deal with those cold temperatures in Australia. That does cause issues around snow, cold temperatures, stiffness of materials, ice. Not familiar with those situations in Australia at all. Generally, floating covers are a much more cost-efficient solution than structural covers, and demand also is increasing. As we speak today in Australia here, we're technically in drought in 30% of the country. Another big driving force here is greenhouse gas emissions to reduce odours, methane, collect methane and flare it, methane being a harmful greenhouse gas, and even better still to harvest that gas and beneficial reuse of that gas. So thinking about applications then, potable water is probably one of the premium applications. It's a vital resource. It's expensive to produce and needs storing carefully, need to avoid evaporation losses, provide a stable temperature environment to maintain water quality, keep the water clean, and usually floating covers provide the most efficient solution for larger storages. Again, this picture here is an example of a potable water floating cover. This example is in South Australia. It's a CSP, a hyperlong cover. Again, similar features you saw before. Walkways, stable platform walkways to a sampling hatch here. Again, the ballast line through here with floats either sides and air vents and so forth. Typical potable water storage cover. Wastewater is the second category I've identified for today. Often wanting to stop gas emissions, often quite unpleasant odours, and also in Australia quite often rainwater is an issue, inventory management. So covers are put on to keep rainwater out of the wastewater facility. And then increasingly, we're seeing interest in anaerobic reactors, covers to help the anaerobic reaction process and harness the gas and use the gas for beneficial reuse. So continuing with that theme of anaerobic digesters, here's an example. It's a facility that we built about 6 or 7 years ago. It's in Queensland, on the east coast of Australia. It's a large abattoir, red meat processing facility, largest in Australia. You can see here's part of the lagoon and the cover. It's a positive pressure cover. You can see the cover's inflated. There's a second lagoon over here as well. Here's a flare when they're not able to use the gas in the production plant. They can flare the gas here. This is the pressure control system, and this I got this off the web. So this article here is claiming that they reduced their carbon emissions by 89%, having installed these anaerobic reactors, and saved $1 million a year in energy bills. So good example of beneficial reuse. So anaerobic reactors and often wastewater facilities have a static water level, so the cover design only has to sit at a constant level. You don't have to worry about the pond fluctuating up and down, but they still need ballasting. You can see here some ballasting feature to provide some cover tension, stormwater trough for stormwater collection, rainwater collection, and cover stability. These covers can be either operated in positive pressure or negative pressure. On the left at the bottom here, you can see here's quite a common example from Asia, where they have very, very simple covers. They work under positive pressure, they're inflated. This example here is also a positive pressure cover design, running at quite low pressures at this stage during commissioning. Anchoring of the covers pretty much like similar to liners, so they can either be, see quite clear here, it's an earthen anchor trench, or they can be secured to concrete beams. Another feature here I want to point out was for gas harvesting. You can see here's a perforated pipe system that runs around the periphery of the storage, and that's to allow the gas to migrate to the edges of the lagoon, and then there's this gas main around the outside, and there'll be collection ports to collect that gas. In terms of constructing these storages, these static storages, there's a couple of options. So they're pretty much always installed onto a full lagoon. You can see in the bottom here, it's a new build facility. That happens to be an abattoir as well. And that's quite helpful because it's just plain water in that particular lagoon. The other three illustrations there, they're active wastewater facilities, so gas becomes a significant health and safety issue. Methane, going to make sure it's extracted from the work front and manage heat and ignition points. This is an example here where the material's being fabricated along the edge of the lagoon. So this is a polyethylene cover. The material's 6-7 meter wide rolls that have been welded together, and when they've been prefabricated, they are then deployed here across the lagoon. Same thing here, being deployed across the lagoon. This on the bottom right is a very large gas harvesting cover. there aren't so many of examples like this, but the covers of this size, there's only one solution. That's to create a work platform that floats in the lagoon, and the materials fabricated on that work platform in the lagoon. So if we now move on to dynamic covers. So the issue we have here, you can see this cart in the top. So when the lagoon's empty, the cover is sitting on the liner on the base of the lagoon. When when the storage is full, the cover is floating on the water, and the area of the cover is smaller. And we use these weights, these ballast weights and floats to take up that slack material, that excess material, and keep the cover surface taut and under control. And that's the whole reason of those ballast lines and float lines. There is an alternative. That ballasting system is the most common. This is an alternative system. It's used a little bit in the States. I've seen a couple of examples of this in North America. And in this case, there's a feature here in the cover, cables in these posts. There's weights or springs, and they just pull on the cover to create tension in the cover. So design features for dynamic covers. So we need this ballasting system. This is ballasted in a double Y configuration. So there's a Y shape here, and there's a second Y shape here. The alternative you saw in some of the earlier pictures is to put those ballast lines around the toe of the dam effectively, and those systems are usually referred to as central plate configurations. We need the ballasting. You can see the cover is pretty smooth and flat. We want that condition for a number of reasons. It allows the water to run off and collect in these ballast lines for removing rainwater from the cover. The cover surface remains cleaner, and they get a better life from a clean cover. Also, when the cover is sitting flat on the water, it has very good wind resistance, actually. It's difficult for the wind to pick up the cover. You don't want too much load though, because you don't want to be pulling the bridging features here in the toe where the cover meets the batter. Again, this is a potable water example. This is EIA material, typical potable water design with stable platform walkways to access. This is a diver platform, a stable platform that will take the weight of the diver, the diver's buddy, and his equipment, and can enter under the cover through this hatch for inspection or maintenance purposes safely. This is the water extraction point, and so the stable walkway continues so that you can access that without having to walk over the cover. You can walk on these cover materials; they're quite strong, but from a health and safety point of view, it's best to have the designated stable walk platforms for routine trafficking on the cover rather than particular maintenance. Again, air vents. It's usually issues around some entrapped air in water going into these storages, and you let the air get out. And again, making the point, this is quite a complex design, and have to bear in mind there are simple alternatives with much less of this feature. They don't look particularly elegant, these simple covers, but they can be quite cost effective in the right applications. Other design features, so anchoring here. Here's a typical concrete beam. The cover's secured by metal battening and bolts. The beam is deliberately set proud of the crest. That's quite effective at helping to keep debris off the cover. Keeping the covers clean helps prolong life. or as I mentioned earlier, they can be just secured into an anchor trench. Stormwater management, rainwater management is quite an important issue. So this cover down here is undergoing commissioning. So these ballast lines are over full of water. They wouldn't normally be like this. You can see the ballast just down here, and that pump's turned off at the moment. It's being flooded with water to confirm the drainage system is working correctly. So this is a floating platform. Inside is this screen. This is to filter any debris from getting into the water pickups. The pickup feature here. In this case, there's an off-cover pump. More common now to have off-cover pumps. Clients prefer not to have to traffic on the cover unnecessarily. So if we can take the pump off the cover, that means one less reason to go onto the cover. And here are sensors, water sensors. So the pumps can be operated in manual mode, permanently on, or as would normally be the case, in automatic mode. And the pumps would be sized, obviously, to forecast rainfall events and make sure we can dispose of sufficient water. Other things, here's a close-up of the diver's platform. Has sufficient buoyancy and stability to carry the weight of the diver's equipment. Usually these things are locked. This hatchway is typically about 1.2 meters in size. That's sufficient for the diver to get in. We've incorporated, in this case, a sampling port also in the hatch, so you don't have to open the hatch and have a hazard in terms of falling into the lagoon to sample water. So moving on to materials, the properties we need are tensile performance, to take the design tensile loads to keep the cover taut, be able to traffic it for repairs and maintenance, and wind loads. Puncture resistance in case things are dropped on the cover, or even abuse, vandalism can be an issue. The dynamic covers need to flex, so it needs flexible material. All of these covers are exposed to UV, so UV performance and chemical resistance. I mentioned anaerobic reactors, particularly fats, oils, greases, acids. Puddle water and chlorine is quite aggressive, and even desalinated water can be very aggressive with geomembrane materials. In terms of the design life, materials, the controlling factor for a floating cover. Often there's a requirement to access underneath the cover. Clients will often want a cover that's removable. That's not feasible, but at least we can provide access for divers or vehicles through the cover and underneath, and some kind of porting system to remove sludge and scum. Life tends to fall into short category or long life. Short, typically 10 years or more, where the focus is around the initial asset cost and would tend to use less expensive materials. Or long asset life, typically 100 years is not uncommon here in Australia. Materials won't last that long. Materials 30, 40 years, maybe a little bit more, some materials. And planned cover replacement cycles are necessary under those circumstances. So looking at the material options, polyethylene is an excellent material, has some very, very good properties, and has a very good price point. The HDPE has really good chemical and UV performance. It comes in wide roll formats. These are polyethylene rolls here, HDPE rolls here, about 6 to 8 meters wide. Can't be prefabricated and doesn't cope well with flexing. It's a good material for static covers. LLDPE has better flexing performance than HDPE, but it's less robust chemically and with UV. Also comes in wide roll format, can be prefabricated. And then we get some specialist polyethylene formulations, some that have been deliberately formulated to provide good flexing performance or chemical resistance, and even some multi-layer systems, so the outer skins are different to the core of the material to create some particular properties. And the scrim reinforced polyethylene available from a particular manufacturer in North America, actually. Polypropylene has been used quite a bit with floating covers, with dynamic floating covers. All these three materials here are scrim reinforced, available scrim reinforced, and that gives us a substantial increase in mechanical properties, which is helpful. Polypropylene has a very good flexing performance. All these materials have good flexing performance, but repairability can be difficult on aged materials. Polypropylene is sort of mid-ranking in terms of chemical attack, resistance to chemical attack, and UV performance. And then the bottom two materials here, I've mentioned before, CSPE, chlorosulfonated polyethylene, or often known as Hypalon, and EIA, which is correctly ethylene interpolymer alloy. It's a PVC that's alloyed with a solid plasticizer, DuPont's Elvaloy, often again referred to as an Elvaloy material. And both materials are premium options. They've got very good flexing performance, they've got very good mechanical properties, they've got good UV performance and chemical performance. Repairability can be a bit of an issue with CSPE as it ages, and CSP does come in narrow roll formats as well, which is not necessarily ideal. So moving on to construction. So particularly for dynamic covers, it's preferable to do as much pre-work in a fabrication facility before going to site. So we would always create shop drawings like this, particularly because premium materials tend to be narrower roll formats. We want to prefabricate those narrow rolls into much larger panels. You can see here's an example of the panels that are being fabricated. In fact, these are the panels for this particular job. The other thing we do that we think is really important is we construct these ballast lines. These geometry controlling features are all prefabricated in the factory. We can fabricate to a much better level of precision, accuracy, and then when we get to site, we'd survey and set them very carefully, and that helps ensure the geometry of the cover is perfect. Obviously, fabricating in the factory means that we're also building in a controlled environment in terms of temperature, sun loading, wind, dirt, dust, and so forth. And so generally the quality of the work is better in the factory. Constructing on site. Typically, the storages would be lined and covered. This example below, you can see that's actually a polyethylene liner. You've got to be careful when installing the cover, not to damage the lining system. I mentioned setting out the controlling geometry. So you can see here that central ballast line's been surveyed and set and put in position, and you can see they're shortly going to put this is a Y configuration ballasting system. They're going to put in this section over here. Again, you can see here this is actually same material liner and cover. So this is actually the liner here. Here's the Y configuration ballast features that were prefabricated in the factory, and the cover has now been brought in and welded to cover panels to this here. Important to build these things to be relatively clean. You can see it's a little bit dirty here. As we construct, we'll be cleaning as we go, particularly with potable water. Depending on the design, we'll often have to inflate the floating cover when it's empty and do a final clean inside the cover and disinfect before starting the commissioning process. Now moving to talk about asset life. It's quite helpful to maintain the asset, keeping it clean, keeping the ballast lines free of debris that will wear and chafe keeping the cover operating as the design was intended to be. It does extend the life. Good maintenance practices are not so common. These examples here are a little bit extreme, but not altogether uncommon. You can see removing this cover here was, we built the cover. It was about 18 years into its life before we actually did any maintenance at all on the cover. And you can see here removing trees. From the ballast lines are all clogged with vegetation here, pulling again vegetation out. These pumps here and these couple of examples, completely clogged with vegetation, not working at all. Again here, the cover very, very dirty, ballast lines choked. So good maintenance practices will extend the life of the asset. Inspections, it's much better to fix any minor repairs early before they become too serious. So regular inspections, keeping a photographic record, comparing 1 year's inspection with the next is best practice. These photographs at the bottom, they're all from inside that storage on the previous slide. And you can see very clearly from a dive inspection where there are cracks or holes in the cover. You can see more clearly than you can by inspecting from above usually. And you can see here splits and holes in the cover. You can see here there's blistering of the material. This material is way past its sell by date, frankly, though it's still in service. To avoid getting into that situation, we can do forensic assessments of the materials. We can make sure that the material still has good mechanical strength, so that it's safe to traffic on the cover, and also we can predict the remaining life of the cover and therefore help to plan any life cycle changes for the cover. Just isolate these pictures. That's the same floating cover again. This is the diver's view of what he does when he's doing his work. And then so some case studies. This is a potable water storage in South Australia. Polyethylene liner. Here's an interesting feature. So we designed these laterals. These can be operated as the inlet system, as chlorine injection system, or just as a recirculating system. The reason being the storage has an inlet at one end and outlet at the other, and the water tends to go straight through the storage and doesn't mix much at all. And so these laterals, they've got ports running along the length of the laterals of a certain size and a certain angle, and so they cause water to circulate inside the storage. And they've also been designed to operate effectively at different cover heights, not just at the one cover height. The now familiar walkways, sampling ports, air vents. Nice. You can see how clean and straight the ballast line feature is. This is related to the factory prefabrication and set out on site. Stormwater pump system here. In this case, the client was keen to have inflation capability. So this feature here at the edge of the storage, that's actually an inflation port, so we can remove that cap, and we put an air pump on there, and then we can blow the cover up, inflate the cover. Another potable water example. So this was a concrete liner with a polypropylene cover. It was originally just a cross in terms of the ballast lines. The polypropylene cover reached the end of its life. It hadn't got to the point where it was fading, unlike those earlier photographs. The concrete basin was in relatively poor condition, so it actually was a less costly and more secure solution to patch uneven concrete and then line the basin rather than try and make the concrete watertight. We've got cushion protection layer on the concrete to help protect the liner. This was built in EIA material. Again, you can see the typical potable water features. Some wastewater treatment examples. These three are all static covers. So this facility here is a wastewater facility in Victoria. Its function is odor control primarily. The gas isn't used, it's just to look after the nearby residents. This was built in multi-layer polyethylene material, specialist material. It's a negative pressure cover. So this is the cover operating in this top photograph here. This is the cover. In case the gas extraction system had a failure, the cover was designed to cope with pressure as well, so that it could store gas for a week without any damage. And this is during commissioning, demonstrating the storage capacity of the cover. Here, actually, as well, interesting note. So for gas covers, got to think about ignition sources again. So here we've got off-cover pumps. These are the water lines here. This is actually going underneath the crest, and the pumps are a safe distance away from the gas cover. You can see here secured to a concrete beam and backing system. These two examples over here, they're both industrial wastewater examples. They're both winery effluent ponds for some of South Australia's finest wineries. The covers, these are examples of relatively lower cost covers, so the clients are happy to replace on a more regular basis. They use less expensive materials. The purpose of the covers is to stop rainwater getting in, inventory management. They don't smell too good, so odor control. But in both cases, they take the gas into their facility and reduce their energy bills. This one was built in both negative pressure covers. This was built in HDP. This is built in LLDP. And last slide, Tim. So here we have. Move this out of the way. Sorry. So here we have a positive pressure cover. This is the cover at its normal operating pressures. This is the cover as the pressure is building. It's an anaerobic reactor. It's a food processing facility, and they take the gas and pump it into the facility to reduce their energy bills. The reactor was built about 20 years or so ago. The cover needed removing because it was failing, and also because it desludged the lagoon. That's a cover off, emptied, desludged, repair some leaks in the liner actually, and then refill and put a new cover on. It was also built in multi-layer polyethylene, and the reason they needed positive pressure capabilities. The plant works 5 days, but the reactor's producing gas 7 days. So at the weekends, they accumulate gas rather than flaring it, that they can then use during the course of the next week. And then this example below is in the very north of Australia. It's tropical climate, very, very high rainfall. It's a landfill leachate lagoon, and there's an issue with inventory management of that leachate because it's contaminated with rainwater. It's also cyclonic, so that adds further complexities in the design. So it's a new build, lined and covered storage. You can see central plate configuration, built in LLDPE. And Tim, I think that's my last slide.
Great, thanks, Graham.
Now we're at the time as well.
Time's fine, Graham. Now we'll start the questions. Graham, first question is, can you discuss methane gas venting options for liners at the bottom of lagoons? In other words, how can that methane that's unfortunately left underneath the geomembrane be vented?
I think there's a couple of things you can do. You want a bit of grade on the lagoon floor. and then we would normally put geocomposite drainage strips that provide a pathway across the floor up the crest and have an exit port or exit ports on the crest.
Okay. And so then there's no vent on the bottom. It's just up on the crest near the anchor trenches.
Yeah. I have come across, Tim, examples where it's not been possible. It's an existing facility with a problem, and I haven't done it, but people have created a hole, a port, and a pipe that comes up through the lagoon. So that can also be done.
Yeah. Okay, Graham, you mentioned using floating covers associated with landfill leachate, which I think is great. And certainly in humid environments or rainy environments, that's a good way to reduce the cost of leachate processing by putting a floating cover over top of the leachate. Any thoughts about covering leachate ponds?
Yeah, indeed. So this, are the slides visible still, Tim?
Yes, they are.
So this is an example here. This one here. So this was a mine site as it happened, and their landfill system. They had a problem with processing the quantity of leachate because of rainwater increasing the volumes.
Yeah.
So that had a floating cover. That's generally northern Australia's generally. I can think of examples. That's one very north. Mackay. We did one in Mackay, which is not quite as far north, but north of Brisbane as well. So we've done probably half a dozen landfill leachate covers.
Oh,
great. Recent.
Great, perfect. Back to water containment situations. What's a typical floating cover in square meters for a potable water system?
So they vary a fair bit. I'd find some. So this is in North America. It's not untypical. This cover here that Doug sent me, about 70,000 square meters. I'm not sure quite how big. Maybe 100,000 square meters would be about as big as they get, probably. In Australia, the biggest is 180,000 square meters. That's a facility in Sydney. That's quite exceptional. It's a huge cover.
Yeah.
They're more typically, the water authorities here in Australia more typically have a dispersed infrastructure. So they don't have one very large facility. They'll have several smaller ones. So they're typically up to, shall I say, 50, 60,000 square meters in surface area.
Great.
A typical size would be 10, 20, 30,000 square meters of area.
Okay. Next question, Graham, is which type of geocomposites are being applied underneath the bottom liner to avoid whale backs or whales showing up? Any suggestions?
Interesting, because a similar question. So generally, the assets that we're dealing with, the subgrades being carefully prepared, and there are no organics in the subgrade, so gassing isn't a problem. If there is a concern about gassing from the subgrade, frankly, a cheap and cheerful biplanar 5mm composite's fine. Doesn't need much capacity at all. We'd typically not provide 100% coverage. We'd typically have strips maybe 20% of the floor covered.
Oh, great. 20%. Good. Next question is polypropylene and CSPE were characterized as difficult to repair during your presentation. What are the challenges repairing polypropylene?
Well, so I'll give you an example, a live example today. So there's a floating cover, polypropylene floating cover. It's about 12 years old. It's on a winery effluent storage. And we want to do some residual life testing. And before we cut holes in the cover, we always make sure that we can get a suitable repair, and we cannot get a repair on this material. To answer your question, that's not always the case. So I think it depends on the polypropylene formulation. It's never that easy, but usually we can repair it. But in this particular case right now, we cannot get a suitable weld. So we're unable to cut samples where we want to cut samples to test the material. CSPE is probably more consistent. CSPE vulcanizes with age and becomes difficult to weld. It's weldable. It requires particular skills to do so that aren't necessarily widely available. It's tricky. You can't, as it gets aged, you have to do chemical welding, gluing. You can't thermally weld it, but it can, with care, be maintained. EIA, benefit of EIA is that it's relatively easy to repair through its whole life.
Okay. Next question, is there any record or estimation on how many floating covers are currently in the world?
I don't know that. I know how many there are in Australia, pretty much. We've got records of going back. The first covers in Australia were built probably about 30 years ago now, 35 years ago. And we pretty much know where all of them are. Top of my head, I'd say in Australia there would be maybe 100. North America, I don't know. Worldwide, I don't know.
Yep. Okay. Second part of this question, I don't know that you can answer this or even should. How old and how big is this market? Maybe let's just answer how old is this market?
In Australia?
Yeah.
So Australia followed North America. The first covers that were installed in Australia, the knowledge, the IP effectively came from North America. The oldest covers in Australia would be around about 35. I think there's a cover that's about 37 years old in Victoria, and that would have been one of the first that was ever built. They really became that earlier technology wasn't so reliable. The materials have got better. The construction methods, designs have improved, as you might expect. And probably about 20 years ago, 25 years ago, was when the market became relatively active, much more active than previously. And it's a relatively active market today. There's a fair amount of, there's probably as much or more life cycle refurbishment activity than there is new build.
Okay. What techniques are used to reduce wrinkles during construction?
That's company intellectual property. So there's a good example. If you can see that picture, that's exactly what you do want to see. That cover is not under very much tension, but it's absolutely perfectly flat and taut. And there's a number of ways you achieve that. The correct design, I mentioned during the presentation, precision construction of all those features and precision set out. And then when you physically install on site, unlike a liner where you just pull the panels together pretty much and weld together and make them relatively neat, and they'll tend to wrinkle and move as the day gets hot and cold. Anyway, with a cover, you have to specifically create the right tension as you construct. There are certain techniques that we use to do that.
Okay. This is another questionable question, but what would be the average price of supply and installation of an EI floating cover for 5,000 square meters? And maybe we should do this in, I don't know, maybe a percentage above something else, or I don't know. I'll let you handle
So 5,000 is a relatively small storage. So the cost gets less with a couple of factors to think about. The cost drivers, maybe I should talk about cost drivers, Tim. So the cost generally gets a bit less with size because you get efficiencies. So a small cover is more expensive to build per square meter than a larger cover. Depends on the sophistication. This picture in front again is a good example of the client wanted a sophisticated design. You can simplify the design, have less function, still providing the protection that's sought, but less other related functions, and save some money there. And the biggest driving force generally in the cover is the material, as the questioner rightly points out. The cost of the premium materials is several times. If the bottom end of the market in terms of price is polyethylene, the premium materials are a number of times more expensive. But you will generally get a better asset life, and the recycle cost is obviously quite high because you've got to remove the old cover, do some remediation, build the new cover. So we've had a couple of examples recently where we've had an outline specification to work with as part of our design and construct contract, and the materials selected by the asset owner have been lesser expensive materials, thinking that would be the most cost-effective way to go. And we offered both what was initially requested and premium materials with overall life cycle costing over an extended period, 60 years. And in several cases, we demonstrated that the more expensive material was the lower overall asset life cost. And indeed, the client then went down that path.
Yep.
Kind of answers the question.
Okay, Graham, during the presentation, you mentioned several different types or polymers of geomembrane, CSPE, PP, EIA or Alveoli, LLDPE, HDPE. Could you give the thickness that is typical for each one of those polymers?
So polyethylene comes for covers, is made from very thin film, 0.3 millimeters, sorry, a mil in the States, 0.3 millimeters, through to about 3 mils, about as thick as it gets, I think, generally. But in floating cover applications, we have done covers at the cheap and cheap end of the market in 0.75 or 1 millimeter covers of that thickness. More typically, we'd be using, we use 1.25 a bit, and one for dynamic covers, and 1.5 or 2 mil for static covers when we're using polyethylene. For the scrim reinforced materials, polypropylene, CSPE, EIA, the mechanical properties are all derived from the scrim, that layer in between the two outer coatings. That's where the strength comes from. And so the thickness of the material is more to do with the chemical resistance or UV performance, and a little bit thicker usually will give slightly better UV performance. So typically the industry revolves around actually 1.14 millimeters, which is a round number of mil thickness. So typically around about 1 mil is most commonly used, 1 millimeter. Some applications go a bit thicker, 1.5 millimeter, and that's to get a thicker coating of the resin over the scrim.
Okay. Currently, what is the percentage of covers being used to harvest methane In other words, of all the covers, is it 10%, 20% for methane?
With of the work that we've done the last 5 years, say, I'd say about a third of the work is methane harvesting. But as I indicated, the trends are generally increasing. We're seeing, in terms of trends, Tim, we're seeing an increase in methane as an issue related to greenhouse gases. And interestingly, in Australia here, water in some applications is moving from the cost of water, stopping evaporation. So I don't have to buy any more water. I want to stop it evaporating. To it's not available. You can't secure it. There are some mining applications where they can't access water, and if they can preserve the water with a floating cover, they can effectively get more processing capacity and therefore more revenue. The economic equation's changed quite significantly.
Okay. HDPE would not typically be used in Europe due to the behavior in relation to with high temperature. What is your opinion? We would suggest a reinforced material instead of HDPE. Do you agree?
I'm not sure I do. Do we know the application?
No application. It looks like just a floating cover.
So this illustration on the right, that's Europe, that's southern Spain, that's HDPE. We use HDPE on static covers in Australia, and our temperatures would be much higher than, or as high as some parts of Europe, generally much higher than Europe would be. And they're perfectly serviceable. You do need to use relatively premium materials with good additive packages that give good UV performance. We usually use materials that are of a higher standard than the minimum GRI GM13 standard. But no, I don't see why you couldn't be using HDP in applications that we use in Europe.
Okay. How many uncovered reservoirs are there in Australia?
Well, there's lots. Where I suppose what I'm trying to think now, where evaporation is. So in for example, oil and gas, where they're storing water that's a byproduct of their production processes, it doesn't have any value. It's actually a nuisance, really. There's no need to cover it. If it evaporates, that's actually helpful. They have to store it and process it. So there'll be lots that wouldn't. If I think about maybe a different way is thinking about how many assets are there that could be covered beneficially. Not that many, actually. Not that many. I'm thinking potable water. Most of the potable water reservoirs in Australia are covered, as an example.
Yeah, I think he's talking about potable. Okay. Next question. Could you elaborate, please, on the central plate design feature, including advantages, disadvantages, and an alternative design type?
Yeah, there's a few things here. So one of the benefits of a central plate is, if I look at this picture here, because you've got two ballast lines effectively, if we had just a Y configuration with one ballast line through the middle here, you're taking half the material slack in there and half there. So the amount of material in that ballast line when the storage is full is less. So you get less flexing in the ballast line. You've got a less deep trough in the ballast line. In the storage such as this this design by Doug here, there'd be an awful lot of material in that ballast line because of the depth. It tells us here, so 18 meters deep. There'd be an awful lot of material in the ballast line. So having two ballast lines in a storage like that is definitely beneficial. That's one of the major considerations. Another consideration is here. I go to the end here. So we deliberately, in this case here, wanted to put the ballast as close to the batter as possible for wind management purposes. That's also important. It's slightly more expensive. If you have a central plate, it's a slightly more expensive solution. You've got more features in the cover. It also means to access onto the cover. So I can find the picture quickly. To access onto the cover, where's that going to be? You can see here the ballast line. So you've got to traffic over the ballast line to get onto the cover. So you've got a bit of a safety issue to deal with. Whereas if you've got a double Y, that's less of an issue. I suppose another occasion you see, sometimes I've seen a number of large storages where they've got the intermediate batter and might put ballast lines on that intermediate batter as well as in the toe. I suppose the easy way of defining the difference would be on generally large storages tend to have central plate configurations, and smaller ones tend to be double Y.
Okay. Graham, during the presentation, you mentioned cleaning between the two liners.
Yes.
Can you elaborate on how to do that?
Yeah. So one particularly of the water authorities we work with, they always want us to, as part of the construction process, to disinfect the liner before they start putting their water into storage, and we then get to the process of getting the chlorine balance right and so forth with the water. So in those cases, we have a two-step process. We'll inflate the cover, so the storage is built but empty. Important that the inlet and outlet systems are correctly isolated. There's no risk of any water getting in when we put people inside the storage. We inflate the cover with air. We put air pumps onto specially designed hatches. There's a special opening as well in the cover, and so we can go inside the storage. And we go inside and we disinfect manually with people. Disinfect with disinfectant water, brooms, pumps, and we clean the storage to reasonably high standard. Then we exit the storage. We let the cover come back down again, and then we'll put a small amount of water in, maybe only half a meter depth, and we'll flush through with relatively high levels of chlorine, and then we'll start doing the proper water conditioning.
Okay. Is Hypalon CSPE still used frequently with respect to environmental issues?
Can you elaborate, Tim, environmental issues?
It just says environmental issues. Maybe why don't we do waste containment first?
Hypalon's premium material and excellent properties, but it is expensive, and that price does preclude it from the more cost-sensitive applications. Its most common application in Australia would be potable water, and there's quite a few applications here where that's been used and still is used in potable water applications. Wastewater tends to be a lower price point cover design system.
Okay. What would be the preferred alternative then to Hypalon?
EIA. They're quite different in terms of their chemistry. One's a rubber, one's PVC, but in terms of the properties that they provide, they've got similar mechanical strength because it's primarily derived from the scrim. They both have good UV performance, both have good chemical performance. In potable water, chlorine resistance is very important. PVC derived materials got chlorine, it's very, very good with chlorine. They're you've got a long debate as to which is the best. Some people would argue that CSG is better than EIA, some the opposite. They both have a place in the marketplace. They're both excellent materials.
Okay. All right, Graham, we're over time, and I think we've covered most of the questions. So before we end, I want to encourage everyone to visit the FGI website. It's fabricatedgeomembrane.com. There's a lot of new information on the FGI website, including the brand new FGI podcast series. So please check it out. Our next webinar is March 24th, 2020 at noon Central Time. And the topic is stormwater management using geosynthetics, including underground or subsurface stormwater management. And the speaker is Terry Sheridan of GeoStorage. So I hope you'll tune in for that. So, Graham, thanks again for a very interesting and thought-provoking webinar. You could see that by the number of questions. And thanks for joining us from Adelaide, Australia.
Thanks, Tim.
Thank you, Graham.